Start. Okay, so good morning. So this is the second talk of today. So JKB, everybody knows, he's probably, I mean, we learned turbulence from him, from like one of the first person to do turbulence in India, I guess, in physics. So this is a pedagogy talk in theme of ICTS that we do a pedagogy talks. So this talk and the fourth talk, Rahul told me, of today, will be pedagogy talk for, especially for young students. So JKB will talk on turbulence, is pedagogy talk, so all yours. Thanks, Pandit.
All right, so here we are. This is sort of time reversed. Dhruvaditya has already given you an introduction, or rather the later part of what would be. So this is going, you have to imagine this is pre-Dhruvaditya. That's the way it was designed anyway. So, all right, what I'm going to talk about are things which you have already seen, and maybe in some details and with some more focus on the calculational aspect, what can be done, or rather what can be honestly done and what can't be done, which let's say maybe all of it. So anyway, it's what we are talking about is homogeneous isotropic turbulence, which is a fluid flow with no recognizable pattern. And therefore, the no recognizing pattern, recognizable pattern obviously means something is amiss with the predictability. And the striking characteristic, therefore, is that the velocity field is some random function of space and time. And the goal would be to find, if that is what you claim, then the question is, what is the distribution, underlying distribution? And that turns out to be very difficult. And so what you settle for is something smaller, much lower level, which is, could I get some class of moments? And the class of moments that we talk about is what you heard from Dhruvaditya a few minutes ago, that velocity difference between two neighboring points raised to the power n, and the average value of that, and can I get a handle on that? And this is the customary Leonardo da Vinci drawing, which you are supposed to show. And here is the drawing which shows vortices within vortices within vortices and so on. And that it is self-similar. If you blow up the picture, then a small vortex over there looks like the whole. So, all right. So in that N which you saw a minute ago, now when it comes to being realistic, you do n equal to 2. So n equal to 2 is not bad, because it is, I mean, v square after all, and that's related to the energy. And so you take the kinetic energy per unit mass and define the total energy in this fashion as a sum over all wave numbers. And writing it in this fashion over here, it is this Ek is what one calls the energy spectrum. That's the definition. When we talk about an energy spectrum, that is what we mean. And obviously, in a d-dimensional space, it can be written as v square by 2 integrated over If it is in momentum space, wave number space, that is, it is this quantity. And the question is, this energy spectrum, what determines it? The obvious answer is that it has to be determined by the dynamics. And what is the dynamics? It's Navier-Stokes equation for an incompressible fluid, which is what our approximation will be, which means the velocities are all much smaller than the speed of sound. So not a bad approximation really in everyday life in very many most situations. And so here is Navier-Stokes equation, which you already had a pretty good dose of, that the acceleration on this left-hand side, the local time change, and the carrying along of the fluid, the advective term over here, pressure gradient, and the viscous dissipation, and an external force which keeps the system going, because we will be talking about a steady state, which is a non-equilibrium steady state. And that's the incompressibility condition over here. So, there is an energy budget. You multiply this equation by velocity, V alpha, integrate, and you get the energy budget. The advective term integrates out to 0. And you have the derivative of the energy is this negative term over here, and V alpha derivative squared, and the driving force giving you a contribution from over here. And as you can see that this chap, or even if you can't, it's not obvious, it should be obvious because of what you heard an hour ago, that this viscosity operates at molecular scales, and the derivative over here has a length scale in the denominator. So it is all very important in the low length scales. And this one over here, where you are actually stirring the fluid and pumping in energy, operates at macro scales. So one at molecular scales and one at macro scales. And your rate of the input, which is this over here, if that equals the rate of dissipation by this term over here, you have a 0 for the left-hand side, and that is your non-equilibrium steady state. And the scales are determined by viscosity and the rate at which energy is being transferred. And so this is epsilon, and here you are, the small scale out of viscosity and the energy transfer, and the large scale once again out of that, but now it is has this form. So this is the sorry, it's a mean average mean velocity V bar, and that's the epsilon, that's the mean velocity. So here is the large length scale, and here is the, so this mean velocity over here gets related to the, you do a little this and that, and the ratio, the viscosity enters, and the ratio of this is Reynolds number to the power 3/4. So if you are, Reynolds number is V average times length scale divided by the viscosity. So if that is very big, you have a large scale where you can imagine that at the small scales, the energy is being dissipated. At these larger scales, it is being, the stirring mechanism is putting in energy into the system, getting dissipated at the short length scales. And therefore, in between, there is a large length scale where essentially distance, where energy is being simply transferred, what you are stirring in is getting dissipated, and the rate at which the dissipation and stirring happens is equal, and therefore the rate at which it is being transferred is also remains constant, and same as what is being input and what is put in and what is being dissipated, and that sets up the Kolmogorov argument. So the existence of this large ratio of the scales of input and the scales of dissipation, which is ensured at a large Reynolds number, sets up the Kolmogorov argument, and which is essentially what that the E of k that we saw goes as k to the power minus 5/3. And here is one of the many pictures of numerical simulation. Here is the E of k, and here is k over here. And you see a pretty nice slope of 5/3, which is what you will be seeing a minute later on the scale. So in this inertial range over here, you translate this into wave vector space, and the L corresponds to some k0, which is a small wave number, and then it is a large wave number over here where the dissipation is powerful, small wave number where you are putting energy in the system, and the Ks that you are interested in lie in between. Energy spectrum is this, and the energy is determined by the wave number, and epsilon, which is everything. It is the input rate, it is the dissipation rate, it is the transfer rate, and then you do a dimensional analysis based on and outcomes this. So epsilon to the power 2/3, k to the power minus 5/3 with a constant c, that is Kolmogorov for you. So this is where one is. And so now what happens if you want to look at the same thing in coordinate space? Well, coordinate space, you look at it, you carry out the same analysis, that it is the difference of the neighboring velocities raised to the power n, and that goes as epsilon to the power n/3, r to the power n/3, with a coefficient C of n for every n, and all the c's are supposed to be universal constants. Now for n equal to 3, actually you have an exact result. Kolmogorov proved this, that C of 3 is minus 4/5. So you have and in all of 3D turbulence, that's the only exact result as far as I know. So it is very important, that, and which you saw in Dhruv talk in the morning. So that's that. And now, well, n equal to 2, you get this, as we said, its Ek is this over here, and C is supposed to be, and the corresponding difference scales as r to the power 2/3. You have real and numerical experiments in d equal to 3. You seem to get a very nice k to the power minus 5/3 with a constant which, as I understand it, the various computations that I've seen, they sort of cluster around 1.7. It is not that somebody says that very confidently that C is this and it can't be anything else. So keep that in mind, that while there is not much doubt about the 5/3 being a good answer, the C being a universal constant is a little bit here. All right. Now over here you see it's n/3, and I'm going to talk about a special case which is n equal to 6. So n equal to 6, which means once again that this, if I look at it is two factors of n equal to 3. So you look at this, and this is n equal to 3, and take another n equal to 3, that gives you n equal to 6. And so now what is an n equal to 3? That is this v cubed, and v cubed, as you saw once again early on, that v cubed divided v squared over t is the energy transfer rate. So ddt of v squared, so that is the energy transfer. And then in terms of t, which is once again r over v, it is v over r. So this epsilon over r can be considered as v over r. And in accordance with Kolmogorov thing, v cubed is like r squared, which means that the energy over here is divide out by r squared here. It is the energy, and therefore energy is r to the power 0, which is like a constant. But this too, the point is, this is where the deviation from Kolmogorov, as I have talked about till now, comes in, that this is not really r squared, and the data experimental is more like r to the power 1.8, and the correspondingly, therefore, the epsilon, the local energy transfer rate correlation is not a constant, but it is r raised to the power some small exponent mu with a minus sign. And this deviation from the Kolmogorov phenomenology, which is what is called intermittency, and for this particular case of n equal to 6, which is this epsilon v cubed correlation, or epsilon correlation, it is important, at least my feeling on that is that it is actually more vital than most, because you can easily relate it to this third order correlation. You can easily relate it to some obvious physical quantity, which is a part of the phenomenology, which is the energy transfer rate. So this mu not being 0 is a big departure, and it would be nice if one were to be able to get a calculation, real calculation for this mu over here, while the higher moments, all the moments which Dhruva talked about are very important, and you can also imagine that the higher you go, the actual calculation would become very difficult. But with this, there should still be some hope that the mu might actually, from the hydrodynamic calculation, meaning from the hydrodynamic equations, doing something which is standard way of doing calculations, and one should have low order non-zero mu. So anyway, that's where one is headed. When I reach that stage, you know the talk is over. So anyway, so what is this Kolmogorov 1941? What you are doing is essentially you are ignoring the fluctuations in the energy transfer rate. So maybe it is what one calls a mean field theory in critical phenomena, and therefore that seems also like the attitude of Kolmogorov and Obukov in 1962, where what they did was that they postulated a distribution for the transfer rate, a log normal distribution. So with mean, and then you calculated with the once you have the log postulated the distribution, you can calculate the expectation values, and once what you do is you compare with the exact result of p equal to 3 and establish this average epsilon, and get to know all the moments in terms of r and epsilon. The low order moments work out reasonably well. At higher orders, you have a problem, which is once again quite strong. All right, so now to actually, how in the world does one do this? If you are not doing it numerically, then what options do you have? So we have to go back to this Navier-Stokes equation once again. And here it is in Fourier space. That's my DDT. Here is the nonlinear term, that's the viscous dissipation, and here is the external forcing. This m, which is the vertex, is the gradient, and therefore it is the k. So it is the projection. This is where the algebra works out. Here is the k multiplied by a projection operator. And then there is this noise random forcing, and you have to prescribe some distribution, and the distribution is taken to be a Gaussian distribution over here. So so you specify the 2-point correlation, and you have them all, and the 2-point correlation is given by delta function in t, delta function in k and k prime, and projection operator, because and some function f of k. So that's the model. That's the model. If you are going to do any calculation, that's the model that you set up. Well, 63 long paper in Annals of Physics, Weil did all the diagrammatics of this very thoroughly, and that. Now, obviously, the calculations, you can set up the model, write down what all the relevant diagrams are, and what, but then making headway once again is a problematic situation. 78, De Dominicis and Martin worked with a situation where they put in a particular form for this f of k, a form which looks like this, 4 minus d minus, this is the dimensionality of space, and y is a parameter that they introduce to make calculation somewhat transparent and simpler. So that's for now. This is all that I'm going to say, and it is towards the end that we'll return to this. But before coming before returning to this, let me clarify what exactly is the procedure for working with this thing over here, and then what kind of problems we run into, and what kind of help one can get from this over here, and where does it take us at the end of the day. So, all right, the only thing, if you are not going to be able to calculate things exactly, you have to do a perturbation theory. So perturbation theory is what we will talk about. So this is essentially what you will find in Weil 1963, and made a little let's say, recast in a slightly modern language, which is not really a great, but it makes reading a little easier, that's all. So you want to do it, the perturbation theory, in the Fourier space in terms of wave number and in terms of the frequency. So the zeroth order dynamics is this over here. It's V0 and it's minus I omega plus mu k square. That is the del del t, that is the viscous dissipation, and here is the drive. You introduce the response function, which is, I change the external forcing a bit, and how does the velocity change? That is the response function g of k omega. And you can see the answer at the zeroth order from here. It is just 1 over del v del alpha, 1 over 1. And so you don't want it in the denominator, easier. Life is easier if you have it in the numerator. So you work with G0 inverse, which is the which is the convenient thing to do because of the diagram, the way diagrammatics unfold. So, all right, you go to the next order. You go to the next order, and well, now you have the nonlinear term come into play. There were two V's over there. And if I want the first order V1 over here, I need to have both of them at the zeroth order. But this will contribute nothing to the response function, because you try to take a derivative with respect to f over here. You pick up and take an average value. You pick up one derivative over here and do an average value. That is but then you are left with one V over here, which is hanging. And when you have taken the expectation value, it is 0. So you get no contribution at this order. So the non-zero contribution comes at the next order, where you have the second order V, and then on the right hand side, it has to be one first order V and one zeroth order V. Remember, when it was 1 over here, there were 2 zeros here. Now it's 2 over here, and it's 1 and 0. And then there is this plus shows that there is also a 0 and 1, but they give the same kind of contribution. Now, if you take a derivative with respect to f and take an average, see, over here, you have the V1 will give you 2 V0s, and one of them goes with the f, and you are left with 2 more. So 3 V0s, one goes in taking a derivative with respect to f, that is gone as a response, and then there are 2 V's left, and now their correlation is non-zero. So you are going to get an answer. So there is going to be an answer at this level. There is going to be a change in the G0 inverse. That change is the new G, the full G, G of k omega. And here is the corresponding Dyson equation, which one always gets in any kind of perturbation theory, that G inverse full is G0 inverse for the quadratic theory, the linear theory, and plus it generally comes with a minus, and I have changed the sign purposely over here because the zeroth order form is minus I omega plus mu k squared. And if I change the sign over here from the traditional negative to a positive, I can write that as a mu effective kn omega k squared, so that this mu effective is like a dressed viscosity. It is changing the bare viscosity, the real physical viscosity that the fluid has, to, because of this turbulent fluctuations, an effective viscosity, which gives you a relaxation rate, which is this, and that's the relaxation rate which you pick up. Mu k squared is the viscous relaxation rate simply because of the molecular viscosity of the liquid. And what does this gamma k of omega look like? Well, you pick it up from here. There are going to be 2 factors of m, because the V1 carries V1 carries M over here. So there is going to be, once you substitute, there are going to be two factors of M. Here they are. V1 also brings in a G, that's where this is, and it gives you a V0, you correlate, and that is what you have over here. So that's the answer for this gamma K of omega, two M's, a G, and a C. And that is what one would call a one loop answer. It is by writing, it would be a exact one loop, a real one loop would have a subscript 0 over here and a subscript 0 over here. That really in this game is not going to take you anywhere. So you do the traditional dressing. So you instead of the G0, the 0th order G, you put a G over here, and instead of the C0, you put a C over here. And so this chap that you have is answer is what one would call a dressed one loop. So a one loop answer, response function, one part of the loop, a correlator, the other part of the loop, and you are using a full dressed correlator and a full response function. That obviously, so which is in, if you draw pictures, this is, if this is your G and this over here is your C, this is the class of diagrams which I'm looking at. You have taken a full G here and a full C here. It is an approximation because what you may, however you may dress it, because there could have been this line over here giving you two more lines, and this giving you a line as well, and you pick up a correlation here, and what you are looking at right now is something that you have an interaction here, you get two lines, and you have interaction here which two lines. These two make a correlator C, this makes a G, and this goes out and meets the other V that is. So there was a V here and a V here, and they are joined by this, which you see over there, and you dress them and get a G and C, which is where. So, but the point is that there would be diagrams which would look like this and this. So there is a 3-point interaction here, there's a 3-point interaction here, and then there is this. And this class is not included. So while this has an infinite number of diagrams, this class over here, it starts with this, and let's put a double line for, so it starts with this, and then you imagine that this line over here is replaced by, let's say, another one of these over here, that there you put in something which looks like this, and that you add that on, and you add every such in a thing on, and you get this dress chap and this over here. And that is what one means by dressing it, the one loop graph, and this is the answer. But it is an approximation because things could have happened with this chap over here, which does not change the scaling, but changes the numbers. Any real numbers that you can get are going to be suspect. But at least, I mean, it is a step which everyone can take very easily and get going. All right. So now you ask the question that is there a scaling solution? So you look for a scaling solution, which means that this relaxation rate that I had has scales as k to the power z. And then there is, I mean, it is after all a function of omega. So there is a scaling function where associated with that. And now there is the other part, the zero frequency relaxation rate is given by this. The other player, which is the correlator, looks like this, and it is a G and a G and F, which is the correlation between the two noises. So G inverse, if you now make the approximation that the bare viscosity contributes very little. So this there is going to be a region, we are in the Kolmogorov region. This is going to be the dominant player. If you make that statement, then you can drop the mu, and here you are, that the G inverse is just the relaxation rate which you calculate out of this perturbation theory, and there we are. So the equal time correlator scales accordingly like this, and you have an approximately equal here because I have ignored combinatorial factors. So gamma of k, the zero frequency relaxation rate, is this integral, and you now match powers of k. The ck integral is k to the power minus m. The gamma k, as we said, is k to the power z. And here you can match, the g is 1 over gamma. So you have a 1 over k to the power z, a k to the power z here. So that's 2z. And then you have a 1 over m, because that is the 1 over m coming from this part. And this part over here gives a 1 over m. So it goes there. So 2z plus m. And what you are left with is this d, which is from here, and m gives you. And so you have the relation that 2z plus m is equal to d plus 2. M is the correlation function power, and z is the relaxation rate. But to find z and m, we need another condition. And this is the energy transfer. So we'll use this as the condition that the energy transfer rate is a constant. So the energy transfer rate, you play the same game. You have the energy transfer rate given by this, and you take a ddt, and you get this, and plus another term which comes from this, and multiplied by a derivative of this, and both taken together give you m, which comes from the this part over here gives you the mvv, and that's the v over there. So there you are. That is what this looks like. The ddt is replaced by this part over here and here. And now you have to find the first non-zero contribution. So the first non-zero, if at this rate you have at this stage you have a 3 V's, and that's going to give you 0. So you have to go one step in perturbation theory. One of the V's has to be expressed in terms of the coupling constant, the G, and 2 V's. Once you have that, here you are, the lowest order transfer rate. You have 2 M's, G, and 4 V's, and the 4 V's become 2 correlators, and you carry out the same accounting which we did before a minute ago, that you pick up a D, 2 D's from here and a 2 from here, so that it is 2m, 2d plus 2, and then you have 1 over m from here, 1 over k to the power m, 1 over k to the power m, that's your 2m, and then there is a 1 over k to the power z, that's your z. So 2m plus z on this side, 2d plus, so denominator has 2m plus z, 2d plus 2 in the numerator, it has to be 0, and therefore epsilon is k independent, and you say, well, there I have 2z plus m equal to, so scale independent energy transfer gives you this. Previously I had this. The total energy is given by this, and all that you need to do now is essentially find z and m, and as soon as you do that, you find that 3m is 3d plus 2, and m is equal to d plus 2 by 3, and it is d plus, so in d my, as soon as you look at the e of E is integral ek dk, ek therefore has this k to the power d minus 1. The c of k gave you this, and therefore e of k is k to the power minus 1. So that's the argument. There was a I still don't have it. I don't have the y. This is an argument without the y. Yeah. This is an argument without the y. So this is just saying that C is like 1 over k to the power m, and the relaxation rate is k to the power n. So no, yeah. Y will come in a minute. So that's it. You have your k to the power minus 5 by 3. And now the point is, what's is there? Where can what are the possible problems? One of the big problems is the rate of energy transfer across scales is independent of the scale, and so. But now you see the energy transfer can be expressed as an integral, and therefore the a number means that whatever it is at the end of the day, the integral has to look like this. Some d to the power d can be anything, not really the dimensionality, but just p, and then a p to the power d. If it was anything else over here instead of d, it would be a dimension. It would be dependent on the wave number. But the point is, it is not dependent on the wave number, and but there is a log which you have to evaluate this kind of. I would have to put a cutoff. There has to be a cutoff, otherwise this integral is going to blow up. And so this is something which was realized as early as 1973. Leslie's book does this very explicitly, and then runs into this issue, and then he uses a trick which says that, look, I mean, this k0 is after all arbitrary, so let's put a distribution on the k0. So you put a k0, evaluate the the cutoff, evaluate the integral with the cutoff, and then say the cutoff has a distribution, take a Gaussian distribution, find the average, and you get a number. That was Leslie's trick. A lot of discussion. So that's all. If you want a present day discussion, it is Mahendra Verma's text, which has a, but here is an issue. Now comes the, and so why is Martin-Dieudonné's? So this is without worrying about the Martin-Dieudonné's picture, where they actually put in a form for this f of alpha. So the Martin-Dieudonné is all that we have done before till now. Is there was no form for f of alpha. We assumed a form for the relaxation rate, that it goes as k to the power n, and the frequency integral of the correlator goes as 1 over k to the power m. Dieudonné and Martin put in this thing over here, and that has a very good reason as I understand it. Kolmogorov in this model works out at y equal to 4. This model is devised to do a perturbation theory around y equal to 0. It would seem a little, I mean, you want it at y equal to 4, and why do you take a model where it is going to be a perturbation around y equal to 0? There is very good reason for this. And now once you do this, you see it is reminiscent of critical phenomena, where the phenomenon happens in d equal to 3, but most of us are very happy to do a perturbation theory around d equal to 4 and use the parameter epsilon equal to 4 minus d as the expansion parameter around epsilon equal to 0. Well, the only difference is you expand around epsilon equal to 0 and want the answer at epsilon equal to 1. De Dominicis and Martin expand around y equal to 0 and want the answer at y equal to 4. So that's all right, but the philosophy, I think, remains the same. So you go ahead and do the same thing once again, and the same equation, and now you have to do a same power counting. It is gamma of k is proportional to k to the power z. Now you don't need any, because the correlator, you don't need any m. The correlator is given. The correlator is G, and this p to the power 4 minus d minus y. G is 1 over sigma. So G is 1 over sigma. That gives you so this z over here. And then there is the minus 2z coming from the fact that there are 2 G's and then this. There is a d plus 2 coming from this, and there is this correlator giving you this. And z is 2 minus y over 3. So this is just the same power counting that I had shown you before, and Kolmogorov is z equal to 2 by 3, and that means y equal to 4. So when so y equal to 4 in the de Dominicis-Martin model is Kolmogorov, and your perturbation theory does very well around y equal to 0. So now the point is that, all right, y equal to 4, I mean, is at some kind of a end point of acceptability. And if you go look back on the critical phenomena, the point was that critical phenomena where there are these large scale fluctuations, and at the critical point, the fluctuations are strongly correlated. Correlation length diverges as t minus tc to the power minus nu. The exponent is half in mean field theory. Experiments give something like 0.63. So there is, so you now go back to the starting point, and mean field theory said that replace the phi, which is the variable phi square, m square is by average value, minimize. So that's the Landau way of doing things, and you pick up a half for this nu, and the Wilson flow is what came in the 70s, that you do this renormalization group flow, and you have the m square, which is the temperature flowing along this. The coupling constant flows like this, and you get which is for there would be corrections but at epsilon equal to 1, you have a much better answer than you had before. But epsilon equal to 0, which is at d equal to 4, you have a problem. That is where what is called marginality, this flow over here has lost, the fixed point is gone, the non-trivial fixed point which you get out of this, the same kind of non-trivial fixed point which Dhruva had been talking about. You have a non-trivial fixed point here for epsilon positive, gone for 0, and now the correlation function, if you try to work out, has a logarithmic correction. It's the mean field answer, which is this t to the power minus half, and then there is a logarithmic correction. All right, so with the Martin de Dominicis model, it was the renormalization group was brought in by Côte and Orszag. So Côte and Orszag, I'll be through in 5 minutes. 15 minutes. Oh.
Question answer included.
Yeah. So, all right. So you now have issue that what is the so what are we going to do? What you are going to do is, what did Yakut and Orszag do in this situation? What they did was they played the game which Wilson played on this Ginsburg-Landau Hamiltonian, and which I'm sure most of you are aware of very well, that you want to treat this, you want the answer at very long wavelengths. The critical phenomena that you are interested in is is a question of the correlation length becoming very big. You are not interested in the small, what is happening at the small length scales, and therefore it is a interesting thing therefore it is interesting to remove the small wavelengths from the problem, integrate them out, get a new free energy which is expressed only in terms of the smaller wave numbers, that is, in terms of the larger length scales. If you try to do that, then it is the M, you are going to restrict yourself, you will try to reduce this to the same structure, and with a new M prime, with a new M which is, let's say, M prime, and a new U which is, let's say, U prime. This will be possible. You see, the procedure, as soon as you do this, you are going to generate all other powers of phi. And this procedure will make sense if the coefficients that you generate with, for example, let's say, with phi to the power 6, you generate this coefficient over here, but this coefficient vanishes if L tends to infinity. If this happens, then you are doing very well. You have a flow for M and you have a flow for U, and that flow will take you to larger and larger length scales, and ultimately when you reach the fixed point, you have a critical, you are at the critical point, you have an infinite correlation length, and you perturb about the fixed point and pick up the exponent nu over here. That's exactly what was done. That gives you, that is exactly what was implemented by Wilson, and it was established that for epsilon, which is d minus 4 minus d, epsilon positive, all the terms like this phi to the power 6, they had coefficients which vanished in the long wavelength limit, and you get this answer which is nu equal to half into. What if epsilon is negative? But if epsilon is negative, so epsilon greater than 0, you have Wilson, Fisher, so on. Epsilon less than 0, you have mean field, which is Landau. And at epsilon equal to 0, that is the no man's land. That's the no man's land where you have to rethink the problem, and the result of it is that you pick up a log over here. So now comes this question that the philosophy over here, which the Yakut Orszag Yakut business was, that you have these large length scales L, and you have a short length scale, let's say, which is eta, and you are making a commitment. Kolmogorov range was K, which is a wave number which is smaller than this eta over here and is larger than the 1 over L. That was Kolmogorov. This picture over here, on the other hand, is like the Wilson picture, where you are essentially looking at the k equal to 0 fixed point. So this is something which one needs to keep in mind whenever one talks about turbulence. It is not as clear-cut as critical phenomena is. Critical phenomena wanted a k equal to 0 fixed point and got it. Over here, the k equal to 0 fixed point is an idealization. You needed something which was in this range over here. You opt for this one because that it's something you can do. All right. So, and if you are lucky, it will work. So, all right, and that's the picture. That's what the thing is. And so you accept that the expansion around this is valid, and you get, as I said, that it is z equal to 2 minus y by 3, and that seems to work at y equal to 4. But now comes the comes the question of the coefficient. You see, this is the last thing that I want to talk about a bit. There was the question in this Kolmogorov business that there is supposedly C, and then there is a k to the power minus 5/3 and the epsilon to the power. And there is this C which has to be calculated. The 2 minus this 2 minus y over 3 for Z is the Z is the relaxation rate gamma to the power, and which is supposed to be 2 by 3 for Kolmogorov, and y equal to 4 gives you this at Z equal to 2 by 3. But the question remains that do I, in this process, the process by which I got this y, which is through the elimination of modes and looking at recursion relation, which is not which was not explicitly done by de Dominicis and Martin, because they were very skeptical, while it seemed a very a good way of bypassing the energy integral. See, you see the point with de Dominicis and Martin, you get a Kolmogorov without actually invoking the picture of the way I did it at first. I used two scaling laws, energy transfer constant and the self-consistency of the perturbation theory, and got the 5 by 3. By putting in this parameter y and using arguments which are self-consistent, de Dominicis and Martin could get the using 2 by 3 as the signature of Kolmogorov. They could see that their model at y equal to 4 is Kolmogorov. But they also realized that if I have to do a calculation, for example, if I want to get this gamma naught over here, then I have to actually do a calculation which is based around y equal to 0. So they could do a perturbation theory around y equal to 0 for the coefficient of this gamma to get the coefficient gamma naught over here, or what in critical phenomena would be amplitude ratios. They would not be picking up gamma 0, but a combination which is essentially this C0 over gamma 0 squared. So it is gamma 0 squared over C0, and they would be getting a number for it. A 1 loop answer or 2 loop there, but it is a number. They could pick up a number over there, and you could do a perturbation theory around y equal to 0, put y equal to 4 when nobody is looking, and you can say that I have got a number. They avoided all discussion about the energy transfer rate because, as they very clearly said, that there are marginal operators in the problem. Y equal to 4 is marginal. So this is what gets related, I think, to the fact that when we did the integral for the energy, it reduced to Kolmogorov, that is epsilon is scale free, in the form that it is an integral which has as many powers in the numerator as in the denominator, leaving the question of log unsaid. So all right, if I were to accept the de Dominicis-Martin business as that, it gives you this. And if you say that the energy transfer rate gives you this with log thrown in over here, then the energy spectrum would, the k to the power minus 5/3 would have a log in the coefficient, and that would mean that this c, which I introduced happily for the coefficient over here, is not a universal constant. In fact, it says that if you look at the data very carefully, or if it is possible at all, then there should be a trend in the coefficient. So, well, this is now just to what about Yakut and Orszag? Yakut and Orszag clearly mention that y equal to 4 is marginal, and yet they do calculate the coefficient C over here. That seems to me to be a conflict of interest that you don't have. As soon as you say y equal to 4 marginal, you have to be you have to get log in it. And well, this could be right, it could be wrong, or it could be what generally in this business of one often sees vaguely right. That is, I mean, if you are willing to close your eyes to certain things, then it's right. Otherwise, it may not be so right. And that allows the field to thrive. So with that, I would like to end. There were a couple of other niceties which are interesting along the way, which I have not talked about. But this is a good time to end if I want to end in time. So thank you very much.
Thank you, JKB, for a nice talk.
I don't really have a question. I just want to thank Jayanta for giving us this wonderful pedagogical talk. And especially for the students, I want to say that if I'm not mistaken, the methods that he's talked about will come in handy when you listen to the talks of Migdal, Jayanta's second talk, and the talk by Leonie Khanin, who will, I assume, talk about these sorts of models, but using the methods of functional normalization groups. Thank you, Jayanta, again.
Any other question? Yeah, I'll ask two questions.
Yeah.
One is Martin's theory.
Yeah.
So integral is, I mean, the dimensional quantity does not require the integral. The integral is divergent. You need RG for getting the integral. Integral for Martin-de Dominicis theory.
Yeah.
Integral does diverge. No, there's a infrared divergence. In the
You mean the integral for this one?
That's right.
Yeah, right. Yes, right. All right. And there is that. I mean, that's. I mean, y equal to 3. The integral that I was writing down happily for this has unfortunately divergence at y equal to 3 when the momentum of this line is very small compared to the momentum of that line. This has been a big problem. Now, the point is, 2 comments on that. I'm absolutely sure that de Dominicis and Martin were very well aware of it, and therefore they focused on a model. I mean, this 1 over k to the power d minus 4 plus y looks like something somewhat strange. But you see, if I use this, then I can set up a perturbation theory around y equal to 0, and that perturbation theory seems to be convergent. Or, I mean, you can imagine that as you evaluate the different order by order, you get answers that it bypasses the problem that Mahendra was talking about by using an expansion around y equal to 0. Y equal to 3 is if I write down explicitly that integral, you will see that y equal to 3 has a problem, as I said, when this part of the is small, momentum is small, and this is all carrying all of them. That is what is bypassed over there by the. Now, is that fair or is that not fair? The answer, my answer to that is that it is probably, I think it is fair, because if you use, when you are, the divergence that comes because of this small momentum here and large there is because you are using you are using an integral which has a Cp, you are using an integral which is like k minus p minus omega prime d omega prime. And in performing the integral, you are making Lorentzian approximations. So you are picking up gamma of k over here, and you are doing it by using a Lorentzian approximation, which means that the G looks like 1 over minus omega plus gamma. If I were to do this problem fully self-consistently, that gamma of k. The light's not. If I use it in the pure self-consistent form, that C of P of omega prime, G of K, K minus P, omega minus omega prime, d omega prime, this integral equation over here, if I solve it somewhat more somewhat more honestly, then the y equal to 3 problem is not going to be there. The y equal to 3 comes up because we take the easy line that it is I'm interested only in gamma of k, and therefore it is omega prime and minus omega prime over here. You put in Lorentzian line shapes which allow you the coupling of large scales over here. The large scales over here are connected to the small scales over here with the same kind of coupling constant as any other scale distribution between the two. If I do it self-consistently, there is a screening out of this particular interaction, and that gives you a finite answer. That I think, I mean, that is my take on it, that why the de Dominicis-Martin business, by working around y equal to 0, essentially handles the dressing of the lines in a manner which is quite interesting. That's all right. That's the answer to it.
Just one comment. So if I do the mode-to-mode transfer,
Yeah.
which we developed, so then this log divergence doesn't come. The integral is finite. Of
Yeah.
course, we assume phi-third, but this integral, energy flux integral, is
Yeah.
finite. And there's no log divergence in that integral.
But if there is no, then nothing can be constant. If something is an integral,
Yes.
and if it is a constant, independent, that's a contradiction in terms. No?
No, it is convergent and use a finite.
It's convergent because you're putting doing it numerically and putting finite limits.
No, well, this is the flux definition in terms of mode-to-mode.
Yeah.
We'll discuss that. So there is no divergence. If I don't exactly
You
follow the
see,
same lines
that I just don't see. If you say that there is an epsilon which is to be expressed as an integral, then and this is a constant.
Yes.
Yeah.
Yeah.
Then and this certainly by power counting comes to that. And this integral, if I'm going to say it is from 0 to infinity.
So there is a catch. There's giver and receiver.
Huh?
Giver and receiver. There is a demarcation of who is giving and who is receiving, and that makes
Which is essentially that you are putting a cutoff.
yeah, the cutoff. But that is the definition of the flux. Flux is.
But if you have then it is no longer, if I have a cutoff, then it is no longer going to be, I mean, you change your cutoff, you would have do another way of, find another way of doing the calculation, you'll find a different answer. I mean, looked at as soon as I use it as an integral without from 0 to infinity, I'm doomed, isn't it?
Actually, I think the flux is going from small wave numbers to large wave numbers.
The flux is going from finite to finite.
That's right.
And therefore, the point is that there is endpoint dependence.
Yes, I think, well, I mean, I'll show you that part. So our integrals are finite with no log correction. Anyway,
Okay, yeah. Yes, sure. Yeah.
Yeah. Anyway, my question is, has anyone, even in simple isotropic turbulence or boundary layer flow or shear flow, whatever it is, has anyone measured the rate of energy transfer between modes, right from the larger scale to the dissipation scale? I mean, has anyone measured it throughout the all the modes experimentally?
Experimentally, that I can say definitely no.
That's the or even over a bandwidth, has anyone measured it in even in simple laboratory flat plate flows?
No,
That would be an interesting experiment.
I don't.
To prove all your theories.
Yeah, I don't think that experimentally it is.
It's not easy. It is not easy. It depends on the physics of the flow, local physics of the
You
flow.
can do it numerically, but you can't really, I mean, do an experiment and say that, look, I mean, here,
It depends on the interaction, local physics
Yeah.
interaction.
Right. I agree. Sure.
So over there, the diagram looks like a bubble diagram. See that diagram.
Yeah.
So in general QFT problems, generally bubble diagrams get cancelled, and what we are left with means non-bubble diagrams with external legs. So let's say
The external legs have been all removed. This is at the Dyson level.
okay.
Right? This is just the, this is at the level of G inverse equal to G0 inverse minus sigma, and the external legs have been gotten rid of.
Okay, so that's what
So, I mean, no external legs in the problem.